Yeah, thanks for inviting me. Like, I consider this like an early Christmas present from Finland. Also the snow, I brought it with me, obviously. Yeah, before I start, how many of you play or have played the guitar? Awesome. Yeah, if you have any questions, please do ask, and I hope you find some new interesting stuff here as well. Before I start, I will just quickly explain who I am so that it helps explain the title of the talk a bit. So I'm basically I did my master's and my PhD at Aalto University on acoustics, and in my master's I was studying a Finnish string instrument. I did some simulations on it together with a maker. We tried to make a louder acoustic instrument with a special structure. And then I worked for my PhD. I worked on concert hall acoustics. But before I graduated, I went to work at Yamaha as a guitar engineer for 3 years. And so a lot of this talk is from my experiences on that during that time. But also now that I'm a postdoc at Uni Bologna, where I work with string instruments. So now I'm slowly getting back to that string instrument and also guitar acoustics. And I did like a little sidetrack on working in the industry for simulating ground-borne noise and vibration on buildings. But I'm also a hobbyist musician. Since I was 5 years old, I play the Finnish string instrument. So that's why I also consider myself lucky that I can combine nowadays in my work my interests in music as well as in physics or in acoustics. And actually a little bit about the current project before we delve into the guitar acoustics. So I work with a group of instruments that is played in the Baltics and in Russia, and in each country it has a different name. In Finland we call it the kantele, but it's essentially a zither like instrument. And the current project where I'm working at in Unibo is actually to do a numerical synthesis or sound numerical model of the instrument for preservation purposes, and to help also to preserve the knowledge of the builders of this instrument. So yeah, I've been doing a little bit of measurements and on the body of the instrument, and then trying to understand how the string and especially the string body coupling point works. So that's what I'm currently doing. But now we go back or to the actual topic, which is the guitars today, the acoustic guitars. And I talk a lot about the steel string because that was mainly what I was working on. But interestingly enough, in academia now, most of the focus is on the classical guitars. I'm not sure why. But a little bit about the premise of the acoustic guitar, and especially the guitar body, which is something that we are very much interested in developing and understanding. The body has a couple of functions in the guitar. You have the aesthetic function. Here you can see the body as a lamp. I mean, you might consider it purely from the aesthetic side, but you know, there's the color of the instruments, especially dark colors are often preferred or reflect the price quality. And then the traditionality, the Taurus classical guitar has a certain shape because of the aesthetics as well. Then we have also the ergonomic aspect of the instrument, like how easily can the musician communicate the idea, how's the playability of the instrument. And then we have the acoustic or structural aspects. And in each of these pictures I try to reflect that if we solely considered that one aspect of the guitar, that's probably how it would look like. But of course at the cross section we have then the guitars that actually exist and are playable. And they also come with the manufacturing efficiency, because we can't obviously build effectively a lot of the designs. So yeah, acoustically, we're going to talk about the acoustics and the structural side of the guitar body, but there are also these other aspects to keep in mind. Yeah, right. But and another thing is that you might say that, okay, but the acoustic guitar has existed for a long time. Like, what is there to research? What is there to design? You know, we have all these great models that are being sold. But if you look at the industry and the innovations and the patents and the NAMSOS, for example, all the time something new is coming with the guitars, be it like new neck designs, new materials, new gadgets you can add to your guitar, transacoustic guitars, a lot of even some new like truss rod designs. So there is a lot from the industry side as well. And if you look at the market of the guitars, okay, it's approximately $10 billion US, and I put here as a reference that the VR technologies, which includes like the head-mounted displays, tracking devices, and so forth, they are about 6 times that. So okay, it's a much larger market, but it's not very small either. Yeah, whereas you look at the research, the academic side of the guitar, here are some of the titles of the recent papers, and I have underscored like some of the important concepts that are now coming up also in research, which is AI based, and there is a lot of simulations, but then you can see geometric and material changes, brace design, and then perceptual evaluation, which is actually, the papers don't come up that often, but yeah, there are some material properties. And then for the usage of the model is, for example, prototyping and sound synthesis. But we are actually living a very active time in guitar research again. The last active time, I think, was around in the 70s and 80s, so we're kind of experiencing a new boom with which has come with the help of the developed like finite element models and software that's commercially available, just like COMSOL or ANSYS. And if I have time, I have at the end I speak a little bit about setting up such a model. What does it entail? But already from this, if we try to put all these aspects into some kind of a order, I like this big picture stuff, is that we have the sort of the holy triangle of generally of musical instrument design or research. We have, on the other hand, we have the physical characteristics, or we try to understand, for example, the modes of the instrument. We look at the admittances, we can do simulations, we can do measurements. And from there, if we understand the physical phenomena, we can bring that to the design specifications, so we can change the bracing of the instrument, change the materials, change the shape. And then from there, we can go on to the perceptual characteristics if we build prototypes based on the design specifications. Or if we know the physical characteristics, such as the modes, then we can do like a sound synthesis based on that. So it doesn't necessarily, you don't necessarily need like a physical copy of the instrument. So we're working on these different domains in the research. So what am I going to talk about? I already said that a bit, that okay, here you can see a spectrum of plucked guitar string at 200 milliseconds. We have the primary vibrator, which is the string. You can see the string modes on the top, and then the secondary vibrator, which is the body. And I'm going to focus on what can we do with this. What can we learn from the spectrum, or from the modes, or from the admittance of the body of the instrument. So I will leave the strings and the coupling to somebody else or to another time, perhaps. Right, but obviously the guitar is much more than the body. We have the string vibrations, we have the neck and the head, and at the other end we have the bridge termination, which also affects the sound of the instrument. And then we have, of course, the excitation mechanism, and then we have some sound radiation. But we look at the body, which is something that the instrument designer or luthier spends a lot of time in. And what are the different aspects that we can study, or what the sort of the guitar body is composed of? We have the different materials. We have the shape and the size of the instrument. We have the bracing design. And then, of course, to that I also add the coupling point of the string, so where the guitar bridge, for example, is located. And then as a final thing, we have the craftsmanship, like how skilled the maker is, for example. But this is a little bit harder to, perhaps to study scientifically, or at least I haven't seen a lot of work done in that yet. So I will not talk about that so much. In terms of materials, we have to start from the fact that wood is a very complicated material compared to metals, for example. The material parameters or the elastic properties are different in the 3 different directions of the wood. Plus, they also depend on how the wood is cut from the tree. So here you can see there's the plain sawn, quarter sawn, and rift sawn illustration there on the side. And usually in musical instrument making, we use the quarter sawn wood. It's the least efficient in terms of like wasting wood. I mean, in terms of using wood, but it has the best. First of all, it affects. It's the least affected by humidity. It bends the least with temperature and humidity changes, but it also has the stiffest. It's also very stiff on the right directions of the instrument. Let's put it that way. And often we use book matching, which you can see here on the mahogany, I think that is. So you actually cut the plank in 2, and then you book match the sides to get like a more or less equal top plate. And then perhaps you recognize this person tapping the plate. So that's a very common way for the instrument makers to understand what the parameter values would be, or how the plate would actually sound like when it's being made. And yeah, the locks can be also, I have just put here a picture that the lock can be quite big, from which you actually then try to make the instruments. Obviously for the guitars it can be smaller, but for a harpsichord, yeah, actually a harpsichord that is full, made of one piece, you rarely find those. It's always glued. Just as the Finnish sitar that I showed you, it's often glued from smaller planks together, and then it might have slightly different material properties as well. So we often assume that wood is orthotropic, but there are cases when it doesn't seem to work too well. Again. Yeah, but a very recent research which sort of tried to understand what would the perceptual effect of different material parameters be on the guitars. So they built 5 different guitars with slightly different Young's modulus and densities on the top plates. So the line here on the graph, it shows you that okay, it has this line is with a constant speed of sound in the material. So you have the A and B in AA, BB, and the CC that actually have a constant speed of sound in the material. And then you have the other on the other axis you have like constant density but different stiffness. I'm not going to play the sounds, but you can go and check the paper and you can actually listen to the sounds. So they asked for, they built these guitars together with, I think it was with Santa Cruz. No, with Taylor, yeah, sorry. They worked with Taylor. And they asked for people for preference, like what's the sound of the guitar that you prefer. And actually the highest preference score was given to the guitar that has the lowest density and also the lowest Young's modulus. So it means that it's a material that can actually bend quite a bit. And that means that it also has a very low, almost like a more bassy sound, because you have the eigenfrequencies of the guitar are much lower. But it was interesting that the speed of the sound, wouldn't really help explain that. So the preference was indeed explained in 2 dimensions by the density and the stiffness of the instrument. So that was kind of an interesting piece of research. So you don't want to make a guitar. It's sort of confirmed that you don't want to make a guitar that's too stiff. People don't like that when you don't have any response from the body itself. That's, I guess, a summary of that research. Then from the shape and the size, of course, now I'm talking about the steel, mostly the steel string guitar, where we have a lot of different options to play as compared to the classical guitar. And, well, a lot of you play the guitar. You also maybe know that you choose the guitar a little bit depending on what kind of music you want to play. But if we look at on the axis of like the sort of the frequency response of the guitar, well, the larger the instrument, the more bassy it tends to be, and the more you use it for strumming and for like accompaniment sound. While a smaller guitar obviously has a more treble response, and you use it for fingerstyle. So you play, when you're designing a guitar which is somewhere in between these models, you try to play a little bit with these 2 axes, or these two qualities for sure. But if we look at it from the acoustician's perspective, yeah, I mean, we have 2 things. We have the Helmholtz resonance, which is sort of the first resonance that the air inside the guitar is vibrating. It's not the first mode of the guitar itself, because it's a combination of the air modes and the plate modes. But you can understand from the Helmholtz resonance that okay, if you have a smaller sound hole radius, for example, the Helmholtz resonance will be lower, so you will probably have a more bassy sound on the guitar. Or if you have a larger volume, then that means that your that is the larger volume. Then that means that you also have like a lower eigenfrequency. Yeah. But then at the same time, you can also look at the equation of a rectangular plate, since we don't have anything better or an analytic solution for a guitar shape, obviously. But you can see that, okay, for example, the length, the dimensions of the instrument are related to the eigenmodes. So the bigger the instrument, the lower the modes would be. I'll talk about the coupling in a sec, like how do we actually couple. Yeah. A little bit more in detail about the shape of the guitar. Here you can see like an OM and a dreadnought frequency response up to 500 hertz. Now there's the simulated and measured. Don't mind about the simulated and measured yet. I'll come to that in a bit. But look at the differences between the 2 figures. Here we see that the dreadnought is a slightly larger guitar, both in area and in the air volume, but also you have the waistline is slightly different. So you see that the first mode of the dreadnought guitar is at lower frequency, it's below 100, while in the OM it's about 100. And also the same applies for the second air mode. And when I was mentioning about the coupling, I really want to point out something, but yeah, like these are the first 3 modes that occur as a coupling of the top plate and the back plate and the air, but they are all dominated by one of the modes. So this is mostly top plate dominated, mostly air dominated, top plate dominated, and back plate dominated. So you can see the back plate mode is not as strong as the rest. But they work in all the guitars in more or less the same way. Also in other instruments that have a sound hole, in the cantele as well, you can clearly see that, okay, there's this 3 modes that are coupled. But what is the really interesting part is then what happens, well, in my opinion, is what happens between 300 and 500 hertz for the guitars. Here, for the OM shape, we have like 3 modes. while for the dreadnought we kind of have two that are dominating, and we see that there is some kind of, because there's a dip, there's some kind of coupling effect. And this is a coupling we can see because of the second air cavity mode, which is not related to the Helmholtz resonance, but it's related to how, a bit like the rule mode, so you have a mode, a note in the middle, more or less in the middle of the guitar. So that mode is actually coupling with some higher order modes of the top plate, and that coupling looks very different whether you have how the guitar shape is actually. So, but this is something that hasn't been researched yet a lot, so that's all I can tell you for now, I think. Right, and then this thing doesn't work again. Ah, yeah, actually here I forgot I had put the animations here. Yeah, I mentioned that, okay, I showed only up to this point now, the modes in the past slide, but and you can make some guesses on like what would make the guitar sound more bassy or have more volume or clearness or brightness or sharpness, and these frequency ranges are actually, and the sort of perceptual attributes are just made by one Australian maker called Trevor Gore, that he was just removing sound or attenuating sound at certain frequency bands on the guitar and then asking people what kind of differences do they hear. So this is not a very scientific approach yet, but this is where we would like to get at some point. How is the frequency response or the admittance of the guitar body, for example, related to the different perceptual effects? And this is something that the luthiers do in their workshop, perhaps even unconsciously. And this is an opinion of one of the luthiers, how he's making it. Yeah, so here are like the coupled modes of the guitar. But actually I don't think that we need to go deeper into that. The important point is to know that, okay, these three are like a air plus the first top plate and back plate mode, and then there's a second coupling section with a higher mode. And the guitar makers like to call these the cross dipole and the long dipole because of the directions that they are, and these are also like something that you play around with. It really doesn't take the reach. Right. So that was a little bit on the shape, and then on the modes, how they can be affected. But then a big thing and a big marketing thing in guitar making is the bracing, the layout. Here are some of the, well, there are a couple of classical ones, the X bracing and then the classical fan guitar, but then there's the Taylor V-shape that they released some years ago, and it was a big marketing thing, at least to say that yes, it improves the monopole radiation of the acoustic guitar. Yeah, I'm not so sure about that, but it's a thing. And actually, depending on the bracing, certain, for example, the cross dipole and the long dipole, then they appear in different strength in the instrument. So in the classical guitar, somehow, I think, yeah, this picture kind of tries to explain that this kind of fan shaping is more prone to the cross dipole movement, so it tends to be very strong. While in the steel string guitar, the kind of long dipole is more, it's easier. So, yeah, that tends to be vibrating more strongly and coupling with the second air mode. So it's, yeah, I noticed that I'm speaking a lot about coupling of modes, but this is like, and mode shapes, but this is kind of the vocabulary of the guitar acoustician, like you look at a lot of the different mode shapes on the different types of guitars to try to make the differences. But obviously, like I said, when you add the string coupling and the strings, what type of strings, etc., that also has a big influence on the sound. Research-wise, I think a couple of years ago, the guys in France, they did a study where they studied a couple of different bracings. So what they did is that the bracing stayed the same, but they varied the material parameters with a model. And then they took averages of the admittances of the instruments after they varied the parameters. So in the bold or solid lines, you can see the averages of those material changes, and you see it doesn't matter, like the material change, the bracings themselves have slight differences in the frequency responses. And again, you see that the interesting part, well, actually this is from what I remember, it might be just the top plate, so it's a little bit different, but yeah. You see, for example, this kind of lattice design has a much higher first plate frequency than the rest of the instruments. So yes, the bracing itself, and as the title says, the bracing itself can have a huge impact on the instrument rather than the material itself. But these are obviously very big differences in the bracing. So if you what we usually do is that in a steel string guitar, for example, you would take the bracing and you would change it a little bit. So that change is obviously not as great as changing the entire bracing. But bracing layout itself does matter a lot. But in the previous slides that I showed you about the materials, then also the top plate material itself plays a big role if you keep the bracing more or less the same. Yeah, and about the bracing, actually, like the point of the bracing is that if you would just have a plate of the guitar vibrating, yes, you would hear the sound, but it would not be actually stiff enough to radiate. So you need to add some stiffening elements into your soundboard. I mean, the soundboards are 2 to 3 millimeters thick. So on the bracing design, you basically look at the height of the brace, and the height is related to the stiffness of the bracing. The stiffness of the bracing is related to the cube of the height. So that's why you can see here this illustration of this like effective stiffness of the bracing when there's some scalloping there. So this is how it looks like normally, but that would be the effective stiffness. So you want to have some stiffness centered around where your coupling point is, so that you have also some structural integrity. Because when you add the strings on the top plate of the guitar, if you don't have enough stiffness, you will end up also breaking the instrument. So that's the other reason why we add the braces. And then the stiffness is slightly dependent on the shape of the brace, so you can also toy with that and study that. And the main thing is the height. And scalloping, so taking some bits and pieces here and there away from the bracing, that helps to spread the vibrations of the plate on a larger area. This is a sort of mathematical paper, but it shows you that if you don't have a bracing, this is the cross section here of the displacement of the plate. So if you don't have a bracing, the displacement is quite concentrated. Of course, the amplitude is higher, but if you add the bracing, you get a much larger spread in the maxima of the vibrations. And this becomes very important at higher frequencies, where where an acoustic short-circuiting can happen. I'm not sure if I have something on that here, maybe later. But yeah, the point of the bracing is also to spread a little bit the vibration maxima around, even though the maxima is a little bit lower. But you can think of it as a larger area displacing, a larger area, like air as well. So then another research on the combination of the bracing and material, which has kind of, it makes sense if you think of it in a practical way, but they have, Alex and his supervisors managed to nicely show that if you you can take a guitar, take it with a certain top plate material, and then you have another guitar with another top plate material. You can make them sound the same if you change or tune the bracing accordingly. So here they took two classical guitars with slightly different specifications. And then they changed the bracing to have the guitar that would have more or less the same vibrational modes, but with different top plate material and bracing. So this is the kind of things that, maybe science can help bring to the makers, so they don't have to make any guesswork. But we can tell them exactly what you have to change to get the same sounding guitar. An application of this would be even in a big production line, working in the guitars. If you can measure the top plate parameters, like elastic constants, but you know that there is some variation between them, but you want to make guitars that sound exactly the same. So maybe the computer can tell you how you have to change your bracing in the production line to get there. So to reduce basically manufacturing tolerance. I have here an image of that actually. Right. I'm not sure how long I have been talking, but I guess I have a bit more time. Yeah. But I'm going to show you this, and then I'm going to go back to the slides that I have, because I'm talking about production line variation. So at Yamaha, we took here's 8 different top plates of guitars from the production line, from the same guitar production line. We measured their mobility. And you can see it's a little bit all over the place, right? It's from supposedly the same wood, but of course also Yamaha purchases wood from many different parts of the world. So it's not always certain that you will have exactly the same parameter values then, or the same wood. But the interesting thing is that when the same top plates are assembled, so the bracing is added there, the guitar is like the sides, everything, the guitar is ready, and you measure from the same point the mobility again, you see that the curves are kind of nicely grouped now. So what does that tell you? That tells you that the guitar admittance, like it's specific to the shape and to the design of the guitar. Not only like the materials are kind of the material varieties kind of secondary in there, which is kind of an exciting result as well. Like you can have very different materials, but the build at the end will give you the same result. So that again sort of confirms that the bracing is a much more important quality of the guitar than the material, in a way. Yeah. But a lot of the results that I showed here are based on doing simulations of the guitar. So I'm going to talk a bit about how we set up such simulations. Of course, we also do a lot of measurements. I don't know if you have done measurements during your studies or maybe after the studies, but a lot of the times we measure the admittance of the guitar bodies with an impulse hammer, with an impact hammer, or we do some kind of model analysis. Either you measure a lot of points with an accelerometer, or ideally you have some kind of a laser scanner. So yeah, those are the two tools that we use to get the sort of the frequency response function, if you will, and then the mode shapes of the guitars. And then for modeling the body response, what do we need? We need to build a geometric model of the instrument. Either, I'll come to that actually in a bit. Then we need to know the material values, so we need to know the elastic properties of our woods. Yeah, we need to do some kind of meshing, or in other methods, voxelization, or some kind of discretization of our system. And then I want to just mention a little bit about perceptual tolerance, because the models are never exactly quite like the reality or what you compare with the measurements, but there are a couple of tolerances that you can take into account. In the simulation methods I was using in the past, we actually did like a coupled finite element fast multiple boundary element method. But nowadays, at the moment, I'm running with my personal desktop a full structure acoustic coupled FEM model with COMSOL. It takes some time, but I can do that. If I'm not interested in real-time stuff, then it's okay. Yeah. But of course, this is a much faster way of running it. First, you can because we assume that it's a linear system, so you can run first the structural analysis, and then you can run the coupling separately. But I'm not going to go into the details of that method. It's one way of doing it. Yeah, there are also many others. You need a geometrical model of the instrument, and then you need to decide what are the essential parts of the instrument for your acoustic simulation. So you can, if you're lucky and you work in a guitar industry, you often have drawings, so you can make the 3D model from the drawings. There are a couple of things that are a little bit of a question marks, like often the backplate is domed. Doming is harder to reproduce in these drawing software, so sometimes you assume that it's flat, and there are things like that. The violin arching is quite hard to also design, especially if you're looking at handmade violins where the sort of the doming or it's not actually uniform, like the thickness of the top plate is not uniform, so that's even harder. So there are things that you have to assume or estimate that you may not be able to measure. You can also put the instrument through a CT scan, and then you can try to get the model from there. I've tried that as well. It is also quite hard sometimes. But yeah, and bigger instruments obviously you can't put in. Like a harpsichord doesn't go into a CT scan. That's a fact. Yeah. But here I have included, you can see there's the truss rod, there are the saddle and the bridge, but it's of course questionable whether all of these have an effect on the vibrations of the body, but you want to be certain that you can include those in. And a lot of the drawing is actually trying to, it's a bit like mathematics. You're trying to think, how am I going to get this shape out? Like the outlines of the guitars, these are not easy to get from the actual guitar to the computer. But also for the makers, when they're designing new layouts or outlines for the guitars, this is quite a daunting task. I was reading one book yesterday that was trying to describe like how to get smooth shapes, because you can't just take a circle of like of a certain radius and take the arc and then start a straight line. It will not look good, and it will not also mesh well if you do it on the computer. You have to use some splines. Yeah, so it's a useful skill to learn if you want to work in this field. I guess that's the point. And then if you work in a company that has a production line of, I don't know, I think they had like 16 different guitars. So if you want to do the same process to all of them, yeah, it takes some time. But I also wanted to point out that here it's not only the model, the geometrical model, but also there are many different woods or materials used in one guitar. So if you want to simulate something as accurately as possible, you need to know the material properties of a lot of different materials in one guitar. And of course it means that they are oriented differently. So wood is orthotropic, like I explained, so you have to make sure that the material properties have the correct coordinate systems. So it can quickly grow up to be very complicated. As for the material properties, there are a lot of different ways of identifying those, not only in musical instrument acoustics, but in general. The most common methods are, some kind of vibrational methods, that you have a thin plate of the instrument that you can excite in some way. But we need to know the density, which you can measure by, at least of your sample material, you can measure by weighting the instrument and then getting the dimensions. Yeah, we need the Young's moduli, the shear moduli, and the Poisson ratios. And actually something that is a little bit challenging for the field at the moment is thinking about the damping of the materials. In this example, I used like a uniform damping ratio. Here are some examples. Usually you measure the plates in free boundary conditions. It's based on some techniques from the 1990s. But now we actually, at Unibo, we developed some methods that you can use also for other boundary conditions as well. So clamped in one side or clamped in all sides. So yeah, usually you need to prepare some kind of samples. The big guitar industries have, of course, they can take an actual instrument and take it apart and then cut these parts as well. I have been involved in destroying some really nice guitars for getting that. So, yeah. But usually the makers have some leftover pieces, so you can use for your models to get this. Okay, the other one I already explained. So there is the manufacturing tolerance, which kind of, if you are trying to make a comparison, well, in my case, I was trying to make a model of a guitar from the production line. So obviously I took from the production line a random guitar and I compared my model against that. But and I'm not sure if the material parameters were exactly correct. So there's obviously some tolerance that I have to deal with. The other interesting tolerance is like perceptually there's been some studies with synthesized sounds on like what happens if the mode frequencies of the guitar body change. Can we perceive the differences? And then if all, like the results are over there, like if all the mode frequencies change, so if the admittance curve is shifted 2 to 3%, that you can already hear. So if at 100 hertz, instead of 100 hertz, the first resonance is at 102, but all the other ones as well, you can hear it. But if only a few modes change, you need a lot more, like 5% or so, to actually hear the difference. So if I'm at about 5% difference between my simulation and my measured guitar, I think it's already pretty good, and that's actually more or less where I am. So now here is the same figure again, but now you can look at the simulated and measured curves. The dashed line is the measured one, obviously, but you can see that the models can capture the overall behavior, but there is some shifts in the frequency response. And also above 500 Hz, it's getting pretty good. But of course, this step is necessary if I then want to use the simulations for studying any of the results that I showed before. And I need to know that my model at least more or less corresponds to reality. Yeah, I mean, that was the frequency response, but then of course we can also look at the mode shapes, like how similar are they. So I measured that guitar, and then I looked at also the simulated shapes, and well, this is the only mode shapes that I am allowed to show from that time, so, but at higher frequencies as well, they look very similar. And something I added here, we usually use this model assurance criterion, which essentially is like tells you how similar the mode shapes are. From 0 to 1. So if you look at the Mach matrix and you see that it's diagonal, then you know that, okay, my mode shapes are very similar. Yeah, that's a common criteria. And then as a final note, most people stop here. So you don't really look at how the guitar is actually radiating sound, and like I explained before, like the damping is a little bit of a question mark. So this is where it comes down to. I have measured the radiation efficiency of each of the modes on the measured and the simulated guitar, and then that's the orange one is the top plate, like average velocity. So you see that the radiation efficiencies between the measured and the simulated guitars, so the blue bars, they are actually quite, I'd say quite different. So there is still some work to be done, especially on the damping of the models, like how to model damping to get to the same sound radiation of the instrument. It does catch the trend, but it's not there yet. Yeah, this is just a slide to show how this simulations were used in prototyping at Yamaha. So we would take the guitar from the line, and then we would, for example, alter the phrasing somehow, and then use the simulations to study how it affects the sound, and then we would actually build them. And based on those tools, we were able to develop some new guitars. Of course, here I have to say that it's a lot of the end results are about scalloping the braces in some locations, which is something that the instrument makers have known for a long time to sort of increase the radiation of the instrument. So it's but it's more about the specific to that model, like what's a good scalloping or whatnot. I've been speaking a lot about acoustics, but like I said, I mentioned before in the bracing, like the problem is not only in acoustics, or you can use the simulation tools to also give you an idea of the structural integrity of the instrument, or how it affects how it's affected by the temperature and humidity changes. So when you're designing a guitar and the bracing as a maker, usually you use this kind of criterion that when you add the strings to the guitar top plate, if there's the saddle, if it rotates about 2 degrees, it's still right, like it can withdraw the tension. But if it's 5, it's already too much, like you have to reinforce the top plate or the structure a bit. And if it doesn't move at all, then you have built a too stiff a guitar. So this is something that you can simulate and then use as a criteria, as an additional criteria to the sound of the instrument, for example. You can also look at how the Strauss rod is behaving in the guitar, for example. But I don't have much on that. So it's a combination of acoustics and mechanics, really. Yeah, I just have this one slide, I think, left. I mentioned a bit like the current challenges, because the simulations is now a well-established and used tool, not only in the industry, but also in the academia now more and more. But we still need to work on the radiation and the damping models. And then another interesting idea is to integrate machine learning into that. There's an example of how we can use neural networks to design violins. So this is a little bit like the example with the guitar with variable bracing. Here, these two examples, you have slightly different body shapes of the violins. The other one is slightly bigger. So the machine learning algorithm told you like where you should carve the instrument to give a similar response to the original one in different colors, for example. So the simulations also help us create a lot of databases for this kind of AI tools. In the industry, we're also looking a lot into alternative materials, because a lot of the materials like rosewood are becoming extinct. So what can we do? What kind of natural fibers or carbon thermal aging has been there for a long time. And then I mentioned a little bit, I showed you this figure from the maker, which tries to establish links between perception and the frequency response of the guitar. But unlike in room acoustics, for example, where we have a lot of standard parameters that are used to sort of give an estimate of the performance of the room acoustically, we don't have these in musical instruments. So that's something that's an ongoing work in general, especially in violins now, but in guitars I hope it will come. And from my experience in the industry, like I would also say that there is a huge thing about how to keep people playing the guitar past the beginner level. This is not so much of an acoustics problem, but a problem of the marketing, or it's an industry problem. But then also understanding what the players actually want. It has to do with establishing some kind of links between perception and objective parameters. But there's a lot of market research going on. What is the next big model that the players, what type of music they want to play, what type of instrument they like. Right, yeah, that's it. Now I can take some questions.